So what's a random walk process? Random walk process just if we have a diffusion source at the center, or we have a diffusing atoms at here, and after time tau, then you can observe this after time tau, you can observe like these atoms make a small r. After n tau times jump, probably it will reach here. So the random walk, the point for random walk actually is here. Is each movement is independent. So that means each jump is independent and nothing related to next jump or previous jump. So we call it independent of previous jump. So you can expect it. So if it is a random walk, each small r actually is random. The direction is random as well. So as long as the n tau is quite large, then if you try to summation all the small r, then you got the capital R, the displacement after n tau times jump. So if it belongs to random walk, then the summation equals to 0. So it turns out that if you try to use the capital R, the displacement after n tau times jump, the capital R to be a indicator to describe the diffusion phenomenon, it will not a good indicator, because you did observe the diffusion happens, but however capital R can tell you this, because you summation this capital R, then you got the 0 results. But however, if you check your materials, the diffusion happens. So we try to find a good indicator to well describe the diffusion phenomena in macro scale. And we try to find a good indicator which is related to micro scale, and to describe the diffusion process in macro scale. So if we cannot use the capital R, then in your textbook it gives you the other choice. Although because the capital R is vector, so random walk, as long as you summation all the vectors, the results always equals to 0. But how about if you use the mean square displacement, you dot capital R with capital R and take the average, we call it a mean square displacement, then this will become a scalar. Scalar, you summation all the scalar and take the average, so it won't be 0. So following parts, we are going to show you or determine or show you whether the mean square displacement is a good indicator to describe the diffusion process of phenomena in macro scale. So we try to dot R and with R. So R squared equals to R, capital R dot capital R. So if you capital is a capital R actually is small r plus R1, small r1 plus R2 plus R3 and so on, plus Rn tau, right? And you dot the other term is also the small r1 plus small r2 plus small r3 and so on. So you will get if you try to dot it, you will get this results, right? R1 dot R1, R1 dot R2, R1 dot R3 and so on until R1 dot Rn tau. And the second term will be R2 dot R1, R2 dot R2, and R2 dot R3, and so on. So finally, you will get the Rn tau dot R1, Rn tau dot R2, and so on. So the diagonal term is R1 dot R1, R2 dot R2 plus. So you can get the first term is Ri dot Ri, and I start from 1 until to n tau. And the rest portion, you can simplify as like this. Ri dot Rj, I think. So probably this is a typo. So it's like if j equals to 1, then I equals to 2, so it will be r1 dot r2. And if j equals to 2, then I equals to 3, so it will be r2 dot r3. So you will get this portion. So if you simplify this, you can get, because r1 dot r2, this is r2 dot r1, so you got the 2 times the rest of part. Okay? Okay, so you can also simplify like this. And next part is we try to average these equations. So try to average it. So the r square root mean square displacement is like this, right? We average the square term. So we average this term, and the second term here, if we try to average it, so you can put the average. We got the mean square each displacement for each jump, right? And you times the, because the summation is I1 to n tau, so you can directly use n tau times the mean square displacement for each jump. And the rest of part, there's 2 factors. You dot the 2 factors, so you got the a dot b, so you got the scalar a dot b cosine theta. Is theta is between these 2 factors, right? So you finally got this result. So we can get the mean square displacement can equals to this one will be associated with the total numbers of jumps. So total numbers of jumps, this term actually is related to how much time this diffusion spend, right, or to cost, right? And this mean square displacement for each jump, the small r, is correlated with crystal structure, because each jump actually is from one lattice point to the other lattice point. So this definitely correlated with structure or varied with crystal structure, right? And then the second term is correlated with cosine theta. So as you know, if we summation a cosine theta term, this term finally has high. If it is random walk, then this term will be what? It becomes to 0. But if it is not a random walk, then we have some value for this term. So we will talk this later. But finally, we got a quantitative description for the mean square displacement. And also this term, mean square displacement, is a great indicator to describe the diffusion phenomena, because it equals highly is associated with diffusion time period and crystal structures. As long as the diffusion happens longer, then you got this value higher. And also, if crystal structure, each jump is longer, then you got the mean square higher value for mean square displacement. It sounds like can well describe the diffusion phenomena in macro scale, and can try to link the macro scale with micro scale. Okay, so this slide, yes, now you have this quantitative description for mean square displacement. Next slide is going to exactly show you how to get the mean square displacement in your cases. So now we assume this is a diffusion from a point source, and it was a, okay, so before diffusion, it looks like this. We have a ball and we have point source at the center of the ball, and okay, this is what we, and after time tau, we observe that the diffusing atoms, the distribution of the diffusing atoms like this. And so This is a large number of particles spreading from a point source through random walk. So it's a random walk. And you also can observe a particle 1, 2, 3. So this green is a particle 1, 2, 3 until NC. So we got the total numbers of NC particles and corresponding locate at R1, R2, and R3. So number 1 locate at R1 from the initial point, so R1, and number 2, particle number 2 is located at R2 and from the initial point source after n tau times jump or after time tau. So how to get the mean square displacement? What's the mean square displacement? You just mention the capital R squared from 1 to n tau that you divided by the total numbers of particles NC. So this is the definition for mean square displacement. And let's explain how to get the total numbers of particles. So you can as long as you know the concentration profile as a function of radius and t, location and t, then you times what? This is a 3-dimensional ball, so you times the 4 pi r squared dr integral from 0 to infinity, then you can get the total numbers of NC. So 4 pi r squared dr is, you can consider, this is a 3-dimensional ball, and 4 pi r squared dr is a share of this ball. So it's a 4 pi r squared, and dr, the thickness is dr. Then this r you integral from this location to infinity, then you can get the total number of NC. The same idea be applied on the top portion. R squared times how many diffusing atoms locate at R1. So how many atoms locate at R2? So the R squared times the weightings, the total numbers, the numbers of total numbers. So it will be a concentration 4 pi r squared dr from 0 to infinity. So you can get the top portion. So I can, for example, okay, let me, okay, so probably I try to use, okay, for example, this is a center. So if I have I have 2 particles, 1 particle, 2 particle, and 3 particle. If we only have 3 particles, so how to get the mean square displacement? Be easy, right? The bottom will be total, and the upper portion will be what? If this is number 1 and number 2 is located at the same distance r1, so you got 2r1 plus 1r3. So this is how we deal with, and this is square. So you got total, we assume just 3 particles, so the bottom is 3, right? And for each atoms, you need to summation the square term, so R1 square. But R1, we assume R2 is the distance from R1 to center is the same with R2 to center, so it will be R1 square. And we have 2, right? So it's 2. And plus now we have R3. It's 1 particle, and the distance from the initial point source is R3 squared. So we got, this is how we calculate. So something, right? This is the values, and you times the numbers. This term will becomes the numbers. How many numbers of diffusing atom locate at specific R away from the initial source? Okay. So as long as you can solve as long as you can solve this equation, then you can get the mean square displacement. So now we try to solve this equation. But in order to solve the equation, the first thing come out from your mind would be how to get the concentration profile of diffusing atom as a function of r, radius, and the time. As long as you got this, then you can just replace this term. Then you can calculate the final results for mean square displacement. So we learned this in lecture 3. The concentration profile depends on what kind of diffusion source case we're talking about. If this is a 3-dimensional diffusion source, the concentration can be expressed like this, and the point will be this 3/2, right? And it's an exponential. So we just directly take this result into this portion. We try to get what's the mean square displacement. So you need to have some mathematics books to help you to solve this equation. So we just grab some results from textbook. This is r squared, and if we take this into here, then this is nothing related to r, right? So we got r to 4 and exponential minus r squared. So r to 4 exponential minus r squared. So use the top portion will be equals to this, and the bottom portion will be r squared exponential minus r squared. So it will be like this, right? Because this is nothing related to r. So you just divided this with this, then you got the mean square displacement equals to 60 tau for 3-dimensional diffusion case. So this result is quite interesting. We successfully to link the mean square displacement with what diffusivity and also the diffusion time period. So as long as diffusivity increase, then mean square displacement increase as well. And as long as you longer the diffusion time period, then mean square displacement increase also. So mean square displacement equals to 60 tau. And some people probably at this moment would ask, how about if it is not a 3-dimensional diffusing cases? How to modify the mean square displacement? You can do the same thing. If it is a 1-dimensional, then you can plot. As you know, the concentration profile is 1.5 here. So you just use this term, and even it is 1/2. So this also is nothing related to r. So you use this term to substitute the concentration term. So what you get is, it will be, this is concentration, but this is 1-dimensional. So the rest part you also need to 1-dimensional. So it's dr. So you use this to substitute this portion. So it will be r squared exponential minus r squared. So it will be r squared minus the upper portion will be like this, and the bottom portion you only have this term. So would be exponential minus r squared. So this divided by this. So you got 40 tau. The same thing play with a 2-dimensional. The concentration profile expressed like this, but 4-dimensional, the integral is, you should integral area, right? So it will be 2 pi r dr. So you use r squared times this term. Then you got r to 3, right? R to 3 and times the exponential minus r squared. So the upper portion will be like this, and the bottom portion will be this term directly. So it will be r exponential minus, so this divided by this. So what you are going to get 40 tau. So here 1-dimensional 2d tau, 2-dimensional 40 tau, and 3-dimensional 60 tau is easy to remember. And now so far we successfully link the mean square displacement with diffusivity and also the diffusion time period. It is proportional to diffusivity and diffusion time period. Okay, but there is something missing here. As we mentioned, actually the purpose finally is try to link the diffusion phenomena which you observe in macro scale with the atomic jump process, which or crystal structure, which you know in micro scale. So now we also only find the diffusivity and tau. We haven't have chance to see any material property related to crystal structure. So next we are going to show you the other approach way to get the mean square displacement. Then I want to show you the results first, then help you to have some idea what we are going to do for next slide. So the concept is that we use the other way to get the mean square displacement, and by using the probability method, then after serious deviation, the probability will be equals to this. So this is what we learn. Mean square displacement in three-dimensional diffusion case is 60 tau, and the probability term we find this mean square displacement is gamma tau mean square displacement for each jump. Then finally, both these are equals to mean square displacement. So this equals to this. So we got the diffusivity can be expressed like the atomic jump rate times mean square each jump. This mean square jump distance. Each jump distance divided by 6. So this is how we successfully correlate the diffusivity we measure or observe in macro scale with the atomic jumping correlated with crystal structure which we observe in micro scale. Okay, so this is the results, but let's try to move back to try to show you how to use the other approach way to get the mean square displacement. So the other approach way is we call the probability. P is a radial probability, which means that the probability you can find the diffusing atoms in your materials, or at least in this bowl. So the bottom portion is the probability you integral from 0 to infinity as a bottom, and the up portion would be the r squared times the probability dr, and also from 0 to infinity. So as you know, if you integral along all spaces, then definitely you can find the diffusing atom. So the probability will be equals to 1. So in order to get the mean square displacement, we need to solve the probability as a function of radius and t. Then we substitute this term, then we can get the mean square displacement. This is how we deal with these questions. So following slide is going to show you how to get this radial probability. And the method introduced to you in our textbook is we use a one-dimensional case to propose what's the radial probability. So we assume also this is a random walk, and we got a row of the atoms here, and this is our start point, x equals to 0. And we assume the atoms, the atoms either make a forward jump, and we call the probability is PR, and this atom also probably will make the backward jump. The probability, we call it is a PL. So this atom only have two choices, either make a forward jump or make a backward jump. So PR plus PL will be equals to 1. And after time tau, as you know, this atom already made n tau times jump, and n tau times jump included nr to the forward direction and nl to the backward direction. So, and after turn tau, we find that this green atoms arrive this location at x equals to n. And we assume this n is positive, so for the forward, and this side will be negative. Okay, so we got some relationship between nr and nl is nr plus nl is n tau, right? The total numbers of jump will be equals to nr, the numbers of forward jump plus the numbers of backward jump. And because finally the atoms arrive here, so nr equals minus nl equals to n. So based on these two equations, we can get nr and nl, right? Okay. And in order to have some more pictures, so we give you an examples. This n is equals to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. N equals to 9. And we assume the total jumps is 11. And the nr must equals to 10. NL equals to 1. So that will satisfy nr minus NL equals to n. nr plus NL, total number is 11, right? So how many possible combination of nr and NL can allow this atom to arrive this location, x equals to 9? How to get that? So what possible is make a 10 right and make a 1 left, or make 10 forward jumps and make 1 backward jumps. For example, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times of forward jump and make 1 backward jumps, then arrive here. Or you can, this atom can make a right and or make forward and make backward. And next is make a 9 series of 9 forward jumps. 9 will be also here, right? So there are how many possible combination of nr and NL to allow these atoms jump here. So you can easily get factorial of 11 over factorial of 10 and factorial of 1, right? So the same concept to formulate the total combination. So you use the omega to represent the total possible combinations will be n tau, factorial of n tau, factorial of nr and NL. As you know, we know the nr can be expressed like this by this equation, and NL can express like this. So we can get the total combination like this. And we just copy the results for this one. This is a total combination, but real probability, you need to times the probability for make a right or forward jumps. So it's a PR and the NR times, and also times the PL and the NL times. Okay, so now you got the probability. So in order to get these results, you need to you can check the lecture note on page 43 to 44. So we can take a log on both sides. Then we can solve this location. It can be equals to this one. So we can get the probability is proportion to exponential this term. You need some mathematics help to get these results. Okay, so now we got the probability is proportion to this exponential term. And what's the n? And what's the n tau? So the n actually can be expressed like if it is a displacement in one dimensional. So it can be equals to n times the mean square each jump distance, right? Okay, so you just substitute this n equals to r squared over mean square each jump distance, because n just here, n squared, so you got r squared divided by this term, so we got, and n tau you put this, as you know, n tau is a gamma tau. So, right? So in order to, yes, you know the proportion, but you don't know the constant. So we put one boundary condition. The probability if you integral all along through the whole space from negative infinity to positive infinity, we got the equals to 1. So you can get the constant here. So this is the you can get the expression of radial probability as a function of radius and time. You take this back to this and take the integral, then you can get the mean square displacement. So after this, these two terms are equal and equal to mean square displacement. So we successfully get the diffusivity, which is describe how fast atoms moves in your material. It will be correlated with atomic jump rate times the mean square each jump distance divided by 6. So now this tells us the phenomenon or what you measure in macro scale in the diffusion process is correlated with gamma is atomic jump rate. So will be related to atomic diffusion mechanism, and also this jump distance depending on the crystal structure, and also will vary with diffusion mechanism. So the right portion actually is related to atomic behavior, jumping behavior. Jump rate, what's a gamma related with? It related to the beta M, energy barrier and temperature, as we mentioned in the first slide, first section, right? So jumping rate is correlated with bond strength, reduced mass, energy barrier, and temperature. And this is the jump distance definitely is highly related to the diffusion mechanism and crystal structure, because if we are talking about the vacancy mediated diffusion process, that means the atoms exchange with surrounding vacancy to allow to diffuse through materials. So the jump distance will be correlated with lattice constant. But if the diffusion mechanism is we call the interstitial mediated diffusion process, that means the atoms jumped through interstitial site. So that will also vary with crystal structure, right? So different diffusion mechanism and corresponding crystal structure and corresponding crystal and different crystal structure will affect the gamma and mean square displacement, and this atomic behavior is the reason why we have a different diffusivity of materials. So you successfully to link the macro scale material property with micro scale material property. So I believe you can explain why your material have higher diffusivity or lower diffusivity. Definitely is in the different part. I mean, it will depends on different diffusion mechanism and crystal structure. Okay, today that's okay. So let's make a quick summary here. And in this part, actually, we give you some pictures. The purpose here is try to link the diffusion phenomenon in macro scale with atomic jumps in micro scale. And how to, first of all, we use the quantum mechanics to tell you how to calculate or estimate the atomic jump rate in specific direction. Gamma prime will be correlated with material property, including bond strength, atomic mass, energy barrier, and working temperature. And we use two different approaches to get to get a good indicator to describe the diffusion phenomena, which is mean square displacement, capital R. And finally, after series deviation, we find that the visibility of material is related to the total jump frequency times the mean square jump distance divided by 6. So successfully to link the divisibility of material with atomic structures and also atomic diffusion mechanism of these materials. Okay, so today ended here.